I want to talk about how I made my first contribution to this open source library called Scipy. You can see the code for it on GitHub here. So now this is a very popular library in Python, probably used by millions of people around the world. Anything to do with statistics, machine learning. If you're writing some code in Python, you'll be importing this library. So how do you even go about making a contribution to a library like this, starting from scratch? So if you want to actually build this from source, it has a lot of C code, even Fortran code, and you need compilers for all of that. And setting all of that up is a big pain, and even if you are an expert, it's probably going to take you a day. Forget about if you've never done that kind of stuff before. So the trick is to take some small self-contained function, and scope your change to that, and that way you can just copy paste it, outside of SciPy, play with it, experiment with it, write test cases for it, etc. So what I did in particular was my change was related to this binomial test method, binom test. So we need to build a bit of background to for you to understand this change. So let's go to the some place where I can write. Um, so first we need to build some context on the binomial distribution. So this is a lot of you might already know this, but basically, if let's say you toss 10 heads, or in general n heads, and the probability of heads is p, let's take an example, zero point 0.5, then what is the number of heads x, right? You'll see in those n tosses, right? And the distribution of that x is given by the binomial distribution. The probability that x equal to k is n choose k, p to the power k, 1 minus p to the power n minus k. So here, I've drawn this for n equal to 10 and p equal to 0.5. So you can have 0 heads when you toss 10 times, 1 head, and so on. The probability you'll see 5 heads is the largest, but you could see 4 heads, 6 heads, etc. So this is the binomial distribution. Now what about the binomial test? So this is a hypothesis test where you don't know the p, right? When we're talking about the binomial distribution, we know the n parameter and the p parameter. Now imagine you're just given a coin, you don't know anything about it. You can toss it some number of times. Let's say you're allowed to toss it 10 times to just test it out. And now you need to make some conclusions about the p parameter, right? Is it a fair coin or not? Is the probability of heads 0.6, and so on. And that's where the binomial test comes in. So what you do is you assume some value, right? You assume some hypothesis, and you say, okay, my hypothesis is that p equal to let's say 0.5, right? And then you say, is the data supporting my hypothesis or not, right? And then your alternate hypothesis is that p is different from 0.5. And then you can say, under my hypothesis, which is p equal to 0.5, what is the likelihood of seeing what I saw when I tossed it 10 times, right? And if that probability is very low, which that probability is called the p value, by the way. If the p value is low enough, you can reject your hypothesis, because you can say, there's such a low chance that my hypothesis would have generated this observation, and the observation could be 10 coins out of 10 are heads. That it's that my hypothesis is probably incorrect. So you can kind of let's kind of just import it in Python and see how it works. So from scipy.stats import binom test, and then it has 3 parameters: the number of heads you saw, the number of tosses, right? So you tossed the coin 10 times, and then the probability under the or under your hypothesis, right? So sometimes that's called the null hypothesis. So in this case I took 0.5. You can see here, if you run binom test 310.5, it will give you a bunch of stuff, and we'll get into some of these things, but the most important one is the p-value, like I was talking about earlier, and in this case it's a 34.3% chance, right? So now you'll see here there's this thing called the alternate, right? Let's get into this. This is basically what the alternate hypothesis is. So the null hypothesis is uh, that the p is 0.5. Now you could only be concerned if the p is less than 0.5, right? Let's say you're gambling and it's a slot machine, and if the p is the probability of hitting a jackpot, and if it's more than 0.5, that's fine, right? You don't you wouldn't mind that at all. But if it's less than 0.5, you want to know, right? You kind of want this test to be to alert you, right? So that's called a one-sided alternative. Here, this is by default you have two-sided, and in that case, what you would do is, for the case of a one-sided alternative, let's say you got three heads, right? You would say, what is the probability of seeing something as or more extreme than the observation I saw in the direction of the alternate, right? In the direction of the alternate. So here, you got three heads. You tossed the coin 10 times, and then you say as or more extreme, right, is 3 or less, right? Because you want to only be alerted if the probability is low, right? So if it's likely to give you two heads, one head, zero heads, right? And so you basically sum all of these shaded probabilities, the probability that x equal to 0 plus x equal to 1 plus x equal to 2 plus x equal to 3, and this gives you the p-value, right? Similarly, you could have the other one-sided p-value, which is if it's greater, right? So in that case, let's say you saw 8 heads, you would go 8, 9, and 10, right? If you want the p-value to alert you when it's greater than 0.5 or greater than whatever you chose for your null hypothesis. And so that's the one-sided binomial test, and that works fine. That was working fine. The problem happens in the two-sided test, right? So now, in the context of distributions that are symmetric, so for example, if you've heard of the t-test for comparing means, right? There, the distribution you are working with is symmetric. So if you have the one-sided p-value, which is typically the tail probability, just like we had the tail probability here, so it could be one tail. To get the two-sided when the alternate hypothesis is two-sided, what you do is you say you have to go on both sides. So remember, in the direction of the alternate would mean now going on both sides. So that would mean you take not only this probability, but you also go on the other side and take the other tail as well, right? And if the distribution is symmetric, then those two tails are equal, and then you can just take the probability on one side and just double it up, right? And that would be your two-sided p-value. But you can't just use this doubling trick if the distribution is not symmetric. And for the binomial distribution, it is symmetric for p equal to 0.5, but for any other value of p, it's not going to be symmetric, right? And so when the p is not equal to when your null hypothesis is not p equal to 0.5, let's say it's p equal to 0.4, you will get some asymmetric distribution. And then what you'll need to do is you'll actually need to find the place on the other side where you should start adding the probabilities. So so now what you would do is, let's say you observed Our intent toss is 8 heads, and then the p is 0.4, so you can't just use symmetry, right? Otherwise you would just say, this is 8, this is 5, so this difference is 3, so I'm going to go 3 here, which is 2, right? And then I'm going to take the probability 8 or more, and then 2 or lesser. But when the symmetry isn't there, then you actually have to go on the other side and find the place, where the probability mass function is equal to the probability mass function of your observation, right? Of this 8, right? The 8 heads you saw, and then kind of sum the areas, right? So then the one sided is simple. One sided would just be 8, 9, 10, right? Some of those, the probability of 8, 9, and 10. But the two sided one would be 8, 9, 10, and then on the other side you would go to the bar which is either equal to 8 or just smaller than 8, right? So like, let's say these two guys are between the height of this bar, right? Which corresponds to the 8. Then you would take this and to the left, right? And you would add all of these probabilities, and that would be your p-value. And what was happening in the Scipy repository was, when you ran this for large values of n, it would actually give you a memory error. Like let's say you passed Binomial Test, like 3, let's say it's 30,000, and some really large number, 10 million, 0.5. It would start giving you memory errors. Now it won't, because I fixed it. But you get the point. So now why would it give you a memory error when you're just passing some numbers in? You're just passing 3 numbers in, right? That shouldn't result in a memory error. So the reason that was happening is we'll need to go to my change, is that the default implementation was creating this array, right? I here was an array, which was the size of the array was n, right? And this array was basically the probability mass functions of this binomial distribution, and then they were kind of looping through this array and finding the place on the other side through this criteria, where the probabilities on the other side need to be summed, and this array would become very large if n is large, and that would actually lead to memory errors, right? And this is probably an artifact of the R programming language, because in R, vectorization is highly encouraged. Everything is done through vectors, and so probably someone copied the code or replicated that code over in Python, and just moved the logic over as is. And you don't need to really store all of that in an array, right? You can just calculate those probability mass values on the fly, so that way you avoid the memory footprint. And then the other thing you can do is by first calculating on the fly, but then what you can do is you can observe that whenever you're kind of searching on the other side, right, you'll see that these probability mass functions are always in sorted order, right? So if you look at the 5, then the 4, then the 3, then the 2, so these will always be sorted, right? So you'll always be at, let's say you're at 8, right, and you want to find the right place on the other side. You're always searching in a sorted array, right? And because it's a sorted array, you can use binary search and make that lookup O of log n instead of O of n. And that's the other improvement I did. I kind of this dumb search that was being done earlier, which was just a linear search, I replaced it with a binary search, right? Created a new method, binary search for the binomial test, which works on not an array but a function. A is a function here, right? And that way you get both a memory and a time speed up. So yeah, that was my first Scipy contribution. I hope this inspires you to make similar contributions, improve the quality of these open source repositories that everyone uses. And thanks for listening.